Hello everyone, hope you all are doing well. So in this video, we'll discuss the last problem of Leetcode BiWeekly contest 102. It's a hard level problem, but the constraints of this problem makes it a relatively easier problem. Let's see what it is trying to ask us. So design graph with shortest path calculator. So there is a directed weighted graph that consists of n nodes numbered from 0 to n minus 1. The edges of the graph are initially represented by the given array edges, where edges of I is basically that the edge is from which edge, from which node to which node, and what is the cost of that particular edge. Okay, meaning that there is an edge from I to I with the edge cost of I. Okay, so we have to implement the graph class. So this is the first function, basically the constructor. So the graph, you'll be given n, that is the number of nodes and the edges. So this function basically initializes the object with n nodes and the given edges. The second function is add edge. This is an edge you'll be given, and you have to add the edge to the list of edges. Okay, edge will be again from to an edge cost. It is guaranteed that there is no edge between the two nodes before adding this one. Okay, and the last one is int shortest path, and you'll be given two nodes, so you have to return the minimum cost of a path from node 1 to node 2. If no path exists, return -1. The cost of a path is the sum of the cost of the edges in the path. Okay, so basically you have a graph. Okay, you have n nodes and you are given a graph with some edges. Every edge has some cost. Okay, like for example, in this case I have 4 nodes and these are some edges. Okay, this says that from 0 to 2 you have an edge. Okay, from 0 to 2 you have an edge, and it's a directed edge obviously, and the weight is 5. Okay, similarly from 0 to 1, from 0 to 1 you have an edge with weight 2. From 1 to 2 you have an edge with weight 1. From 3 to 0 you have an edge with weight 3. Okay, this is something that is given. Now now this is done. Okay, now someone will call the shortest path. Okay, we'll be calling the shortest path. Tell me the shortest path from 3 to 2. Okay, from node number 3 to node number 2. So this is node number 3, this is node number 2. So what is the shortest path? 1 2 3. So this is 3 plus 2 plus 1, that is 6. 6 is your output. Okay, now the second thing is again shortest path from 0 to 3. So just see, from 0 to 3 there is no edge, there is no possible path. Okay, hence you return -1. Then you add an edge, and that is from 1 to 3 you have an edge with weight 4. So 1 2 3. Okay, so this is added from 1 to 3, this weight is 4, and now you have to tell what is the shortest path from 0 to 3. So 0 to 3, so this will be 2 plus 4, that comes out to be 6. This is what we have to do. Okay, so yeah, mostly an implementation based problem. Now let's see the constraints, how that will be helpful in devising our solution. So the number of nodes is 100, right, and the edges is obviously n into n minus 1. That is the maximum number of edges that you can have, because in that case every node will be connected to every node. Edges dot length equals to edge dot length equals to 3. Yeah, that means every edge will basically have 3 attributes: node 1, node 2, and the edge and the cost. Okay, this is also done. The edge of the cost of an edge can go up to 10 raised to power 6. There are no repeated edges and no self loops in the graph, and at most, just see this, at most 100 calls will be made for add edge, at most 100 calls will be made for shortest path. Okay, so now what happens, there are again two options. Okay, the first thing is you have to construct the graph. Okay, let me directly show you the code, because that is self-explanatory. This is the first function that I have. Okay, rather this is the constructor. Okay, so this is my graph, this is the adjacency list that I create. Okay, so there are two options. You can use the extra algorithm or you can use Floyd-Warshall. Why I have used Floyd-Warshall is because that is easier to code, and the constraints that I have in this problem will basically very easily pass for Floyd-Warshall as well, right? So when you do Floyd-Warshall for the first time, that means the first time when you calculate it for all the edges, so that is big O of n cube, right? So if you have 100 nodes, that will be cube of this, so 10 raised to power 6. So in the constructor itself, what I have done, I have n nodes and I have these edges. Okay, so this is my graph, new of int. So graph of I comma j will have what is the minimum cost. Okay, of what is the minimum cost to travel from node number I to node number j. That is what Floyd-Warshall says. Okay, so arrays dot fill graph of I max value, suppose 10 to the power 9 is the maximum value that I have taken. Now just see how simple it is. So the cost of traveling from I to I will be 0. Obviously you are on the same node, right? Now what are the other things? So these are the edges that I have. Okay, what it says, from edge 0 to edge 1 there is an edge. Okay, from node 2, sorry, from node 1 to node 2 you have an edge, and the cost of that edge is 2, right? You initialize it, you do this. Now you run the Floyd-Warshall algorithm. This is, you'll do this just for the first time in the constructor, and then you will be doing it for add edge. I'll tell you. Okay, now here what I'm doing, this is the general template of Floyd-Warshall. What you do, this is the intermediate node. Now you are calculating the minimum cost from every I to j. Okay, this is I, this is j. I am calculating from graph ij. Okay, what is that equals to? Math.min of already existing value, comma, graph of ik and graph of kj, sum of these two. Meaning I have to calculate the distance from I to j. Okay, what I do, I take an intermediate node k, and for every possible k I say that my current cost from I to j is suppose this. Okay, now can I reduce it? Can I take any possible k such that distance this plus this is less than existing distance? Okay, you do it for all the k's. That means all the intermediate nodes you can do it. So this will give you the minimum cost, right? You do this. So this is your first function, that is the constructor. Now the second function is add edge. Okay, so an edge will be added. Now again this edge will be from node 1 to node 2, you have a cost. Okay, so what you will do, while adding this, since the constraints are low, what I'll do, suppose you add an edge, you have a graph, like I'll talk about this one. Yeah, this one. So let me erase it. Yeah, let me erase it. Now just see here, this is the edge that was added. Okay, so what are the cost of which edges or which combinations will change? Okay, which edges, which combinations will have a change or possibly may have a change? Okay, so this is the edge that I have added. Okay, so all the I comma j will have a change. Suppose there is an edge here, okay, and there is an edge here. So if I have added an edge from node 1 to node 2, all the edges that is terminating here, all the edges that are terminating here, okay, and all the edges that are originating from here, terminating in node 1 and originating from node 2, can have a change because I have added an extra edge here only, right? This will not have a change, obviously, right? This will not have a change because there is no path from here to here. But since you have added this, so all the edges that are converging at node 1 and which are going out from node 2 can have a change. Okay, so now what I have done here, when you are adding an edge, okay, so you calculate, you update the cost of all ij such that the graph of ij will be math.min of graph of ij, that is already existing value, and graph of I and edge of 0. Okay, what did I say here? Graph of I and edge of 0. Okay, edge of 0, right? That is how that will make a difference, right? And similarly, yeah, here I was, and graph of edge of 1 plus j. Okay, meaning this is node 1, this is node 2, you have added an edge here, so all the edges that were coming here and all the edges that were going out from here can have a possible change. So what I am saying, I am saying that for a particular I comma j, okay, for a particular I comma j, you can update the value, whatever is the existing value, the minimum of existing value, and graph of I, suppose this is a node, okay, graph of I and edge 0, this, okay, this plus this plus this, getting it? So this is graph of I edge 0, this is graph of edge 1j, and this is the new edge cost that you have added. Simple. You do it for all the combinations, okay, only related to this edge. When you do it, what you have done is you have incorporated the changes that will be done after adding this edge. Okay, now the last function is shortest path. You are given two nodes, you have to return what is the shortest path. So if the shortest path between them equals to max value, that means there is no path between them, so you return -1, else you return whatever is the minimum distance, right? So the beauty of this code is we have used Floyd-Warshall. Just see, this is the code of Floyd-Warshall, and while adding the edge, we are just doing it, we are running an n square loop, so it will not time out. Getting it? Now n square is 10 raised to the power 4, and you can call it at max 100 times, so that is 10 raised to power 6. So it will pass well within the allotted time, right? The other option is obviously the extra algorithm that you can have. Now the extra will be very much similar, okay, but again it's relatively, I would say, cumbersome to code. That is why I've used Floyd Warshall, right? So yeah, I hope you learned something new from this video. Do support it by giving up thumbs up. Do subscribe to the channel, and in case of any queries, mention that into the comment section. If you want to get connected, you can connect with me on LinkedIn. The link is mentioned in the description. Yeah, thank you, take care, bye bye.